Hello students, imagine you're tuning an old radio. By just turning the dial, the circuit inside magically picks one frequency out of thousands. That magic is made possible by the LCR circuit. An LCR circuit is simply a resistor, an inductor, and a capacitor all connected in series to an AC source. The source voltage is V of t equals Vm sin omega t. Since they're in series, the current is the same through each element. But here's the twist, each element's voltage is out of step with the others. The resistor's voltage is in phase with current, the inductor's voltage leads, and the capacitor's voltage lags. The result? A fascinating dance of voltages, all adding up to the applied source. Now students, let's bring everything together and learn how to construct the Phasor diagram for an AC circuit with resistance, inductance, and capacitance. We start by choosing the current Phasor I as our reference. So, I of t equals Im sin omega t plus phi. Next, we plot the voltage phasors across each element. The voltage across the resistor, VR, is always in phase with the current, so it lies parallel to I. The voltage across the inductor, VL, is 90 degrees ahead of the current. And the voltage across the capacitor, VC, is 90 degrees behind the current. Now, the source voltage is not simply in line with any one of these, it is the vector sum of VR, VL, and VC. That's why we need vector addition to find the resultant voltage phasor. As you can see in the diagram, the combination of these voltages gives us the overall supply voltage V, which makes an angle phi with the current. Quick insight, Phasor diagrams are powerful tools because they let us clearly visualize the vector addition of out-of-phase voltages. Instead of juggling equations, we can use geometry to see exactly how the circuit behaves. Students, we know resistors oppose current through resistance, inductors through inductive reactance, and capacitors through capacitive reactance. But in a circuit with all three elements, how do we describe the total opposition? The answer is impedance, denoted by Z. From the Phasor diagram, the net voltage across the circuit is written as Vm squared equals Vrm squared plus Vlm minus Vcm squared. Now recall the relations. Vrm equals Im multiplied by R, Vlm equals Im multiplied by XL, Vcm equals Im multiplied by Xc. Substituting these, we arrive at Im equals Vm divided by Z, where impedance Z equals the square root of R squared plus XL minus Xc squared. So impedance Z acts like the effective resistance of the entire LCR circuit. Quick insight, impedance combines both resistance and net reactance into a single powerful tool, making AC circuit analysis far easier. Now that we understand impedance, let's explore the phase relation in an LCR circuit. The phase difference between voltage and current is given by the expression tan phi equals XL minus Xc divided by R. This tells us that the phase angle depends on the balance between inductive reactance and capacitive reactance. If Xc is greater than XL, the circuit behaves like a capacitor and the current leads the voltage. If XL is greater than Xc, the circuit behaves like an inductor and the current lags behind the voltage. And if XL equals Xc, the inductive and capacitive effects cancel out, leaving only resistance. In this case, the circuit is purely resistive and current is in perfect phase with voltage. Look at the Phasor triangle shown here. R is the base, XL minus Xc is the vertical side, and the hypotenuse gives us the impedance Z. The angle phi clearly represents the phase difference. Quick insight, whether current leads, lags, or stays in phase is entirely controlled by the difference between inductive and capacitive reactance. Students, now let's connect the concept of reactances with the time graphs of voltage and current in an LCR circuit. If the capacitive reactance Xc is greater than the inductive reactance XL, the circuit behaves like a capacitor. In this case, the current waveform leads the source voltage. It reaches its peak earlier. On the other hand, if Xc is smaller than XL, the circuit behaves like an inductor. Here the current waveform lags behind the source voltage, it peaks later. And finally, if XL equals Xc, the inductive and capacitive effects balance out. The circuit is purely resistive, and the current waveform is perfectly in phase with the voltage. Take a close look at the graphs. The dashed curve for current either shifts left, meaning it leads, or shifts right, meaning it lags, depending on whether the circuit is capacitive or inductive. Quick insight: the phase behavior of an LCR circuit smoothly shifts from leading to lagging as the balance between inductive and capacitive reactance changes. Students, let's move to one of the most fascinating phenomena in AC circuits: resonance. Resonance occurs when the inductive reactance, XL, becomes exactly equal to the capacitive reactance, XC. At this special condition, the two effects cancel each other, and the circuit behaves as if only the resistance is present. The resonant frequency is given by omega naught equals 1 divided by the square root of LC. This is the frequency at which resonance occurs. At resonance, the impedance Z reduces to just R, and the current amplitude becomes maximum, given by Im equals Vm divided by R. That's why the current shoots up at resonance. Look at the graph. Notice the sharp peak at omega naught. That's the resonance point where the circuit draws maximum current. Here's the real-world connection. Resonance is the principle behind tuning radios and communication circuits. When you turn the knob of a radio, you are actually adjusting the resonant frequency of an LC circuit to match the frequency of the station you want to hear. Quick insight: resonance is like hitting the right musical note. When the natural frequency of the circuit matches the applied frequency, the response is maximum. Alright students, let's work through a numerical example to solidify our understanding of the LCR circuit. We are given that the resistance R is 200 ohms, the capacitance C is 15 microfarads, the applied voltage V is 220 volts, and the frequency F is 50 Hz. Step 1. We calculate the capacitive reactance Xc. Using the formula Xc equals 1 divided by 2 pi Fc, we get approximately 212 ohms. Step 2. We find the impedance Z. Substituting into the expression square root of R squared plus Xc squared, the result comes out to about 292 ohms. Step 3. Let's compute the current. I equals V divided by Z, which gives us around 0.755 amperes. Notice how the current is reduced because of the high impedance. Step 4. We calculate individual voltage drops. Across the resistor, VR equals I multiplied by R, giving 151 volts. Across the capacitor, VC equals I multiplied by XC, which is about 160 volts. Now here's the key insight. Although VR and VC individually add up to more than the source voltage, their phasor sum equals exactly 220 volts. This is because voltages in AC don't add arithmetically, but vectorially. So the takeaway is clear. In LCR circuits, phasor diagrams are essential to correctly account for how voltages combine. This example highlights why impedance and phase relations are so important in AC analysis. So let's wrap this up. In a series LCR circuit, the effective opposition is called impedance, combining resistance and reactance. The phase relationship depends on whether the circuit is dominated by inductance or capacitance. Current leads in the capacitive case, lags in the inductive case, and is in phase at resonance. At resonance, the current is maximum, limited only by the resistance. This principle is the backbone of tuning devices, filters, and many applications in communication systems. I hope this session clarified the working of the LCR circuit. In our next discussion, we'll see how power behaves in these AC circuits and what the concept of power factor really means. Stay curious and see you then.